Hello, hello. Let's start our lecture, the last lecture in topic C.4 about resonance and damping. Just a note before we jump in, I'm going to throw some math at you in this. And some of the math is not going to be some stuff that you won't get to until you get to HL year 2. There'll be a little bit of calculus and differential equations mentioned. I'm just showing it to you so you begin to hear those terms. We're not emphasizing the math. This part of this topic is just about the ideas, the vocabulary and ideas of damping and resonating. You will not have to solve for anything quantitatively using these equations. So there aren't any formulas on the sheet. So don't get intimidated by the math. Just follow along. And if you don't understand every step of it, that's okay. Okay, looking for the big ideas here. So let's start with what we already know about. We're looking at an oscillating system and something that's vibrating or moving back and forth. And we'll go to that old familiar spring mass system. So here we have a mass on the end of a spring. We move it out to some displacement x past equilibrium. Equilibrium is the place where x equals 0. And then the spring exerts a restoring force, pulling it back to equilibrium. So the formula that describes this is Hooke's law. F equals negative kx. So if x is positive, it's negative because the force is pulling back in the negative direction. Now, if we put this together with Newton's second law, F, the force is ma, so forces cause the mass to accelerate. So ma is equal to negative kx. And what I can do then, I can divide both sides by m, and I can write this as negative k over mx. So the acceleration is proportional to the displacement. This is the definition, if you remember, of simple harmonic motion, where the farther you pull something back from equilibrium, the more acceleration you have working your way back. And here's where I'll throw the calculus in. Even if you haven't learned calculus yet, you know that velocity tells you how quickly your position changes. And then acceleration tells you how quickly your velocity or your position. Let me say that again. Acceleration tells you how quickly your velocity changes. So they're describing rates of changes of these things. So in the language of calculus, we say that velocity is the derivative of position with respect to time, that it tells me how quickly position changes. And then acceleration is the second derivative of position with respect to time. So this may be a new notation to you, but d squared x dt squared. This is the symbol for the second derivative. So it's another way of writing acceleration, the rate of change of the rate of change of position. And that's going to be equal to negative k over m times x. So the solution to this function is we're looking for a function that's equal to the negative of its own second derivative times some constant. And when you get into learning derivatives in calculus, you'll learn that the sine and cosine functions are equal to the opposite of their second derivative. So this is called a second order differential equation because it has the second derivative and the function in it. The solution to this function, again, we're just doing some hand waving here, but the solution to this function is the familiar equation for simple harmonic motion. So a is going to be equal to some trig function, say cosine, x is equal to a cosine omega t. And if we were to make a plot of that right here, a is going to be the amplitude of the function. So we'll have positive amplitude and negative amplitude. And as we let this thing oscillate, there's no friction. It's going to look something like this. It's going to oscillate between positive and negative amplitude over and over again. And this is going to continue for forever. It'll be this cosine function. Now, in this cosine function, we've got the omega, our angular frequency, the rate at which this thing, so that's what the where refers to, where omega is equal to 2 pi times the frequency, because every oscillation corresponds to 2 pi radians, and is equal to, for the spring mass system, the square root of k over m. And again, that's on the IB data sheet. We looked at that earlier with simple harmonic motion. But you can see that the k over m is coming out in here. It's the constant in my trig function. It's going to be related to the constant. There's a square root in there. Again, I'm not worried about deriving this rigorously. This is something we've seen before. What I want to point out, though, is that this frequency is unique to this spring mass oscillator. It depends on how stiff the spring is and how big the mass is. And once you've set those two values, there's going to be a frequency and then an angular frequency at which this thing will tend to vibrate or oscillate. It's not It's not optional. It's not going to oscillate at just any vibration frequency. If you let it go, this is how it's going to oscillate. And so this is what's called the natural frequency of the system. We could use F naught. It's like a fundamental or natural frequency. That's referring to this frequency here. So it's helpful to think about, a spring mass system or really anything that wants to oscillate as having ways that it desires. Speak of it of having a desire to oscillate. So how does a spring mass system want to oscillate? It wants to oscillate at its natural frequency. Now you could grab it and shake it at some other frequency, but the spring isn't going to cooperate with you. This is the way that it wants to oscillate. So this is just review. We've talked about all of this before. What's new now is we're going to ask the question, what if there's another force present? What if we have a resisting force like friction or air resistance? In other words, what if this is realistic? It's not just going to oscillate forever. It's going to eventually slow down. Energy is going to be lost. And the term for this in oscillations is called damping. We have a damping force. Any force that resists my oscillation and slows it down and takes energy away is a damping influence. So sometimes this is bad. Maybe you want something to vibrate and you don't want it to dampen out. And other times it's good. Maybe you have like the suspension of a car where you've got wheels and then springs that attach it to the body of the car to kind of absorb bumps and shocks. But you don't want to feel like you're riding on a pogo stick when you sit in your car. You'd kind of like that oscillation to die out and die out quickly. You might deliberately add damping. So suppose that we add some kind of a fluid and a piston and cylinder to create resistance. And you can see what that might look like in the model here. We've got our spring mass system oscillating back and forth. And then we've got some kind of a piston right here that's generating friction, or maybe compressing a fluid or moving a piston through a fluid, and creating some resistance. Okay, so while this thing experiences resistance, let's say that resisting force, so we'll write our equation again for the force. We've got the force of the spring acting on this thing via Hooke's law, but now we have another resisting force that's proportional to how fast the thing's going. So the faster it goes, the more it's being resisted. There's some constant B, which is related to the drag, maybe the properties of the fluid or the size of the piston, and then V is how fast it's moving. So if we do the same kind of thing we did before, we got MA equals negative KX minus BV. And if I divide both sides by M and recognize that acceleration is the second derivative, again, I get the rate of change of position. It's the same as we had before, as negative K over mx, but is also equal to negative B over mv. And so I actually have a more complex differential equation because V can also be written in terms of x. V is the derivative of x with respect to time. It's the first derivative. It's the rate of change of position, whereas the second derivative is acceleration. So we're looking for a function that satisfies this, that is the function minus its first derivative is equal to its second derivative. And again, there's all kinds of techniques for solving these kind of things. And once you get some calculus under your belt, I'm just going to tell you the solution. Okay? The solution for this function that satisfies this looks something like this. X equals A e to the negative B over mt cosine omega t. So, that's kind of funny, and you just have to take my word for it. But if you take this function's first and second derivative, it does satisfy this expression. So what's going on here? Well, I can see that I still have a cosine function. The thing's still going to oscillate with damping, but as it oscillates, here's the amplitude, and this whole term right here, a, and this exponential term, this is the amplitude. And write that down here. Amplitude is this term right here. And the amplitude has an exponential decay term in it. As time gets bigger, this thing is going to begin to shrink towards zero. So for instance, if I were to, again, right up here, say this is the amplitude of oscillation A, but then at time equals 0, e to the 0 is just 1. I'm going to start off with an amplitude A, but that amplitude is going to decay. So let's draw an exponential decay. I'm going to draw it as a dotted line. And this is going to be an envelope for my trig function. Its amplitude will decay over time. So this dotted line is the function x equals a e to the negative b over mt, just the amplitude of the cosine function. And the amplitude is going to do that both as a positive and a negative value. So down here I've got negative a, and it's going to be mirrored down here. It's going to be decaying towards 0. So what this does is this forms a boundary for my oscillation. It's still going to be a cosine function, but its amplitude is going to shrink, as shown here. So I'll draw this, and notice that as I draw my cosine function, it's being bounded by the decaying amplitude. So it is continuing to oscillate, but the oscillations just get smaller and smaller as they begin to approach 0. So the amplitude decays exponentially. And this decaying amplitude represents a smaller and smaller oscillation. So I guess the big takeaway here is that this is energy loss. We're creating heat in the damper, in the piston. And so it's taking energy away from the oscillation. Also of note, something else changes too. This omega is not actually the same omega. And again, this isn't an equation you have to know or have memorized, but you do need to know the basic relationship. It turns out for this particular function, omega is equal to the square root of k over m minus b squared over 4m squared. So think about what this means. The m is the mass, and then k is the spring constant, and then b is the damping, the drag that's being produced, the damping constant. Now remember, if you look up here, omega was equal to root k over m for the simple harmonic motion. And this is the same omega if there's no damping. If b is equal to 0, I just again get root k over m. But what I want you to notice is as you start to add more and more friction to the system, what it does is we're subtracting something from k over m. So it makes omega smaller. So we could say that when you add damping, not only does the amplitude get smaller and smaller, but the rate, the frequency of oscillation becomes less as well. It doesn't oscillate as many times per second. And that should make sense intuitively. It's being resisted by something, so it can't make as many trips back and forth every second as it would if nothing was resisting it. Okay. Again, you don't have to actually plug any numbers into these equations. You certainly don't have to derive them or even use them, but you have to understand that the amplitude is decaying and that the rate of oscillation is decreasing. And this represents energy loss from the system. The other thing that is important IB-wise is the vocabulary of 3 categories of damping, 3 different levels of damping, from a lot of damping to hardly any damping. And you can think about them. I got the 3 bears right here. It's like the 3 bears of damping: the papa bear, which is overkill; mama bear, which is not enough; and the baby bear, which is just right. Okay, so let's start with mama bear. Mama bear, her food, her chair is too soft, her food is too cold. It's just the not quite enough. So if we have some damping but not very much, IB calls this lightly damped, but sometimes you'll see underdamped. So those terms are interchangeable: lightly or underdamped. A lightly or underdamped oscillation is going to look something like this, where you're going to let it go. It's going to look like that decaying cosine function, smaller and smaller. And basically you see the thing vibrate 3 or 4 times back and forth and then eventually die out. That's lightly or underdamped. Okay. Heavily damped, let's say you don't want something to vibrate back and forth. So you just put tons of friction into it and you pull it back and you let it go. And because there's so much friction, it barely moves. And in fact, it moves super slowly. And so maybe it just goes, oh, so slowly back toward equilibrium. And in fact, maybe it never even gets there. If there's enough friction, it might even stop before it reaches there. Okay, so this is what's called heavily or overdamped. So much damping that it prevents oscillation from happening. It never gets to equilibrium, so it can go back and forth, but it just takes forever to get there. And then lastly, we have the sweet spot, the baby bear. And in the sweet spot, what's called critically damped is we have just the right amount of damping in the system so that it doesn't bounce a bunch of times, but it also doesn't take forever to get back to equilibrium. And in a critically damped system, is going to do something like this. It's going to get to equilibrium as quickly as possible, and it's going to stay there. So from an engineering perspective, this is often a sweet spot. Again, like you think about the shock absorbers in a car, you've got these springs connected to your wheels and you've got the pistons creating damping on the inside. You want those suckers critically damped. So your wheel hits a bump and then it pops right back to equilibrium and stays there. when your shocks start to get worn out and they start to wear smooth and they get less friction in them, then you start to become underdamped and your car gets bouncy, too bouncy. So those are 3 terms you need to be familiar with. The second thing we're looking at in this last activity is basically the opposite. So damping is about taking energy away from an oscillator. Is it possible to put energy into an oscillator and make it oscillate more rather than less? And that's where we get forced vibrations and something called resonance. So we can ask the question, what if a periodic driving force is applied to an oscillator? Now, it's important that it's periodic. So if something's vibrating back and forth, you can't just give it a steady push. That's just going to shove it in that direction. You've got to give it a push and then step back and wait, and then give it another push and step back and wait. And every so often or every period of time, you give it another push. That's a good example is pushing somebody on a swing set. There's a rhythm with which you push some. You don't just push steadily on somebody. You wait and you push again, and then you wait and you push again. That's a periodic driving force. And so if you do that, if you exert a periodic force, will you lose energy, which would be negative work, taking energy away where the force is against the motion, or will you gain energy, which is positive work? Again, if you consider pushing a kid on a swing set, if you push with their motion, that does positive work. But if they're coming toward you as you push, that's going to be negative work, and you're going to slow them down. Okay? So what really matters, whether you add or subtract energy from the system, we'll say is the rhythm of the driving force. Can we get in rhythm with the way that the thing wants to oscillate? In other words, with its natural frequency. So here's an example over here. We can see a mass. We got our spring mass system. Suppose you're holding the spring mass system and you're wiggling your hand up and down and making this thing bounce up and down. Okay. So the wiggling of the hand is the driving frequency. We'll call that F drive, the rate at which it oscillates up and down. And then that's making the block get tugged up and down at that rate. But is it the way that the block wants to oscillate? But remember that the block has a natural frequency. And for a spring mass system, and again, this is on the IB data sheet, previous topic is the 1/2 pi root k over m. So it depends on the stiffness of the spring and the mass of the system. This is its natural frequency, the way that it would like to oscillate. And let's just make up a number. Let's say this particular spring mass system wants to oscillate at 10 hertz. Doesn't want to oscillate slower. It doesn't want to oscillate faster. So if you wiggle your hand up and down at 10 hertz, you're going to really make this thing happy. And every time you push, you're going to be in rhythm with it. You're going to make it oscillate. And every push is going to give more energy to it. But if you push down while the mass is moving up, you're going to actually act to slow it down. If you get out of rhythm up with it, you're going to be taking energy away. So when you get in sync with it, we call this resonance. We make it resonate. Resonance occurs when the driving frequency is close to or equal to the natural frequency, the way that something wants to vibrate. And when that occurs, the energy is added with every push. And we can draw this in the form of a graph, the amplitude of the oscillator. So suppose this guy tried wiggling his hands at different rates. So that's different driving frequencies. And there's one particular magic rate, right? Remember, for our spring mass system, what it wants to oscillate with is 10 hertz. So if we start driving it at 10 hertz, that's going to create a lot of amplitude that we're going to keep adding energy to it. But anything less, we'll get less than oscillation. So we get a graph something like this, that the closer our driving frequency gets to 10 hertz, the more energy we end up adding to the system. And we can make it resonate at that particular frequency. There are all kinds of examples of this, and it's sort of, it can be more complicated than just the spring mass system with one rate at which it wants to oscillate. Think about musical instruments. Think about the standing waves that we've talked about before. A lot of times what we'll do is we'll have something and we'll just start giving random vibrations to it. So think music, for instance. So here we've got a trombonist, And as he blows into the mouthpiece, his lips are kind of blowing and just making a bunch of random vibrations in the mouthpiece. And as they blow into the mouthpiece, he's got this column of air in the trombone, and there's certain frequencies, not just one, but a whole bunch of them called harmonics. And the harmonics are all natural frequencies. All of them are frequencies at which that air would like to oscillate. And what's going to happen is those random vibrations of his lips is that certain ones are going to be driving vibrations that are going to match a natural frequency. And those are going to get super loud. Those tones and their harmonics are going to come out on the trombone. And there'll be some other vibrations, but they're just going to get washed out. They're going to not produce resonance and not produce noticeable amplitude. And so the ones that resonate are amplified and become noticeable. So even just like the hollow body in a guitar, it's going to take the random vibrations of the strings and it's going to amplify those that form the harmonics for that body of the guitar, for that air cavity. I'll flip over to the last part here. We could end by asking what happens if we look at the whole picture. What if we have, we're driving something, we're adding some force to it, but there's also some damping present as well. So first of all, if there's no damping whatsoever, which of course wouldn't happen in real life, then every time you push something, you add more energy to it. There's no limit to how big the amplitude can get. It'll just get infinitely big. So the no damping case, we would have this peak, just would skyrocket up to infinity right at the resonant frequency or the natural frequency. Okay. And what I need to do is kind of center this peak above the F naught. I don't know how well I drew that there. Let me go a little bit better. There we go. So this would be, we'll say no damping. Perfectly frictionless oscillator that's being driven. And then when we start to add some damping to it, then we start to get a curve with a set peak. There's a limit to the amount of energy that the thing can give. Okay, so here we have our light damping or under damping. And as we start to add more and more damping, we'll notice two things, that this curve will get lower and lower, but it's also going to begin to, its maximum is going to begin to drift to the left as we add more and more damping. Okay. So these would represent heavy damping. And it's not too uncommon for IB to ask questions about this kind of thing. And you can see that the frequency we're trying to match is the natural frequency. We kind of draw a line down here, but then that frequency is starting to get smaller. It's starting to kind of drift over here toward lower frequencies. And we can say that the effect of dampening or damping on the oscillation or of the resonance is that it widens the curve. It's not as narrow of a curve. So if there's little damping, you really got to nail that frequency in order to get it to resonate. But it's a little bit more forgiving. When you have dampening, you can just kind of be close to it and still make some resonance happen. Okay. It lowers the maximum amplitude. You're not going to be able to add up to infinite amplitudes because friction is taking energy away. Okay. And it also lowers the natural frequency, the resonant frequency. We talked about that before. The rate at which a damped oscillator wants to oscillate is slower than the undamped oscillator. So that's why the peak is actually drifting toward lower frequencies. And this kind of thing might show up on the test. It'd be good to know how this curve changes with damping. And these are kind of the three things you need to be aware of. So we'll end this lecture with just a simple example. Again, no math, right? No equations. You don't have to plug anything into formulas. We do need to know the terms and vocabulary. So this refers to the Millennium Footbridge in London. It's a real place. There's a picture of it there. When they built this thing, they found when people started walking on it, it started to vibrate and shake. Okay. Now, the force of a person walking on this bridge is pretty small. So what is the name of this phenomenon? And if this was an IB test question, they're fishing for the word resonance. We get some resonance, and we have to explain why the bridge is resonating. Why are we getting these really big amplitude oscillations, whereas the footfalls of the people are really small? So why are those tiny forces making this big bridge shake around a lot? Okay. So we could say that it must be because the walking gait, meaning the rate at which people's feet fall on the bridge, must be close to a natural frequency of the bridge. And so what's happening is, even though the driving forces are small, is they're very close to the natural frequency of the bridge, and so the amplitude is growing. So whenever they designed this, they didn't think about how the bridge would want to vibrate in terms of an oscillatory system or what harmonics it might have, and they kind of found out accidentally that that matched pretty well with the way people walked on it. So what's the solution to this to keep it from resonating? We're asked for two measures here, which engineers might adopt to reduce the size of the oscillations on the bridge. One possibility is to basically add damping to create more friction in the moving parts. And adding damping, creating resistance between parts that would move or twist, creating more air resistance, creating more friction between rubbing surfaces. That's going to reduce the resonant effect. That's basically going to drop this curve down so that we don't get as high amplitude of oscillations. And the second option would be to change the natural frequency of the bridge so that it doesn't match the way that people want to oscillate. And if you think about modeling it like a spring mass system, you would probably change that by adjusting K or M, adding some mass to the bridge to give it more inertia, or putting a different type of reinforcement in it to make it stiffer, or maybe taking something out to make it less stiff. Changing its stiffness or changing its inertia would both have the effect of changing its natural frequency. And then what's happening, if that's the case, is you're having a driving frequency that doesn't match that natural one, and you don't get big amplitudes for that reason. All right, that's the end of the discussion on damping and resonance. You're ready to jump into the activity now. Good luck and have fun.